Good afternoon. I'm probably the first Australian accent you've heard today. We're both Australians, and here's Angus, and what he's holding is a piece of magic in the sense that this piece of material, when you put it outdoors under the brightest sun you can just about come up with, doesn't get very hot at all. In fact, it stays colder than the outside air. Okay, so why are we looking at such things, and what's the science? I'm a physicist, but I'm also a materials scientist. I get involved in architecture and all sorts of things. And what we're really about is looking at the environment around us from an energy perspective. And ultimately, it's about solar radiation and the radiation from the atmosphere, and about the radiation that goes back out through the atmosphere. And we have to learn to harmonise those things to what we as humans respond to. Now, a lot of what we've had today is about visual imagery, but a lot of the magic that happens in the world is about the stuff we don't see. And I'd love you artists to get more into the world of thermal and near infrared, because that's what I'll say a bit about. Anyway, our ultimate aim on this talk is about producing roofs that any cool cat can sit on. Okay, this is the basic philosophy that we've sort of evolved over many years of working in the areas of solar, environmental, building science, and so on. And we start off as physicists in very much optical and thermal, but also solid state science. From that, we develop a bunch of, in the yellow circle, different types of materials we work with. We'll go for anything that will achieve the sort of goals we're after, optically and thermally. And then, then when we come up with successful responses in these materials, we'll then put them into appropriate technologies. And we've worked to some extent, we've heard about, even touched on algal at one point, how to keep the little bugs working better by keeping them cool. And even beyond that, we're now moving into urban and global systems, and that's very much what this cool roof business is about. Okay, well, this is where I live and work. It's not in that blue, that's just one small segment of Sydney, which some people may know. And you'll see this is a thermal, there's lots of thermal imagery out there now, and I'll have a bit more to say about that as we go through. But the areas in red, this is taken in the early hours of the morning between 1 and 5 a.m. And you see that the bright red areas are roads and the CBD, or the yellow areas. And they're staying well above ambient temperature right through the night. And that is not good. It's not good for human health. It's not good for energy use and so on. There are some areas down the bottom corner which are blue. The roofs there are cool. That happens to be near the airport, and some of the roofs we've been involved in looking after or coating are down in that area, but many more throughout Sydney. Sydney is a much bigger area than that. So basically, we're interested in, particular here, in cool roofs or ultra cool roofs, in fact, in the latest material, and to some extent cool walls, because we've had a lot to do with windows and paints as well for walls. Okay, now turning to Australia's other second largest city, Sydney wins, like New York wins here. And in any city you go in the world, if you look at the thermal images, and a lot are available now for most places from satellites and UAVs and all sorts of things, and you compare it to the visual image in the daytime, and this is a daytime image on the right under bright sun, a nighttime image, the same area, and the visual image. And this is pretty typical. You see there's one roof there that is genuinely cool. There's one area, one roof I'll point out, and I haven't got time to go into details, that is a tricky one, because thermal imagery you have to know how to interpret. And that is not a cool roof. It's actually somewhat hotter than that one there. Okay, sticking with the idea of imagery, this is where we get into the nitty-gritty of thermal imagery and what it can tell us when we're applying these technologies. And I'll come back to the underlying science first. A lot of work we did up to this particular piece of work where Angus was holding was in the paint area, and there's some very interesting things you can do to improve the performance of paints. All whites are not good solar reflectors. So you have to look at the whole spectrum. The 50% of the solar energy we don't see. And then, so this company, a small company we've helped along in Sydney and done other work ourselves, is painted this large roof. Partly painted, sorry. This was new metal decking, but it partly semi-new. It had corroded, it got a little bit of oxide on it. And you notice the contrast between left and your left and right. Now, this is what's interesting about this thermal image is not only is the one that hasn't been coated very, very much hotter, the infrared perspective changes. And the one on the left is bright blue, no matter how far you look into the distance. That means it's cold. Now, the other thing is it's the same temperature out, and so is the one on the right. So what's going on? Well, that's an interesting piece of thermal physics, which most people aren't aware of, but it's something we knew we had to deal with in this work. Basically, radiation coming off as a function of angle is very, very different, especially as you get to high angles. Okay, so we're dealing with the environment, we're dealing with the atmosphere, and then we're dealing with the sun. We're dealing with both, all at one time, in one material. So just to understand the atmosphere a bit, here's the heat flow at night. It's all infrared. We don't see it, but it has an enormous impact on the way we live and our life and so on, and it's the thing we're most worried about at the moment. The big red arrow is the amount going out, and the other stuff is what comes back to us. Most people don't really understand global warming, but it's basically that incoming arrow, how big it is. And there's a bit about solar energy there in the total to put it all into perspective. So what we're doing in this technology, we're trying to get just the right to control both what goes out, what comes in, and the sun in the daytime, which I'll show in the next slide. So we're trying to control all these things in one piece of material. So here's also another view of this, now opening up the sun. This is to sort of imagine this, that's the sun hitting the spectrum hitting the outside of the Earth. And the things that really are so important are these gases in the atmosphere. Water vapour and CO2, and a few other bits and pieces, but they're the key ones. Now, the interesting thing is that these are trace gases. On average, if you condense the amount of water down, it comes down to in the atmosphere above us, it comes down to a few millimetres. It's not much, but it has enormous impact because the water that absorbs the sun, we have water in our bodies and we cannot get too hot. If that wasn't there, we'd be in trouble. The CO2, on the other hand, is the big problem. And what's interesting, the black bits are they block everything that hits them, those areas. And this is all, the bottom axis is just wavelength, so we've got a whole bunch of spectrum we're looking at. And these things, the black things absorb, and these are just radiation intensities. But the other interesting thing there is this blue band here, and that takes us straight through to outer space, and that's very important. Some radiation gets reabsorbed in the atmosphere, that's what a greenhouse is. Some comes back, just like a glass pane, and some goes out into space. But some of our out goes directly into space, and if we start causing problems there, we block that heat flow to space, and that's what the issues are all about. Global warming and so on. So, here's what our supercool material does in both a thermal and a normal sense. Now, the right image was, we didn't get the exposure quite right, and I have to say a little bit about it. The sun, by the way, if you see a lot of ads for solar energy technologies, you'll often see a sun like that sitting above. But in reality, the sun is usually facing the solar system, whatever it is, and that's a composite image of the sky taken at the same time with the thermal and the real. Now, that magic material that Angus was holding is just there on the right, and it's not giving off any radiation. So here we are. We've gone down very cold. The green line is it's sitting under the atmosphere in very hot sun, 1,060 watts per square metre. We're looking at the whole angle space, directional space, and spectrum space, and these figures tell us how well our system's performing. They have to be the same colour all the way up, and we have to have sharp transitions from either high reflectance to high absorptance or intermediate. And you have to get all that right. And finally, I have to do a small movie, if you'll let me run it, which shows something dynamic. This work, the things I like to say is that cool roofs and ultra-cool roofs will have to be a future necessity in our cities if they're going to be livable. Among many other things, we're going to have to change. And in the broad sphere of sustainability, you have to harmonise these environmental flows with what we need as humans and what animals and plant life needs. And finally, the optical principles, which I haven't had time to go into, but the same principles can be used in all sorts of things to get both thermal and beautiful visual effects. This dress on the right happened to be produced by a fibre that's made with the same optical principles in part, not totally, as our super cool roof material. And it's happened to be by a designer in our Faculty of Architecture and Design, and she used it from a fibre made in Japan. And we can adapt that to do thermal things with clothing as well, totally in polyester, not with metals or anything. So I'd love, if this works, there's a video. So that's my thank you. Now, will it go? Here we go. It's only 30 seconds. It's been sped up 4 times. And you'll see, the total lapse is 2 minutes. And what happens dynamically, I had to mute this, as I was just telling some of the people outside, because the guys taking it, they weren't physicists, and they let out an explosive or two in the middle because it was a moment of awe as that thing turned cold from a very hot. Thank you.